Okay, let's say P is 8101, it's a prime number, and alpha is 6, is a generator of GP, and we are looking for x satisfying 6 to the x is congruent to 7531 modular of P. Okay, first of all, we need to find the factorization of P minus 1, which is like that. So we are looking for some numbers is congruent to x itself for each of these factors, and I just name it like x2, x3, and x5, which is easier to figure out is for what modulars. So first of all, let's decide the x2. Then we are looking for x is congruent to x2 for modulo 2 squared. So at this moment, temporarily, we just put q is for that prime and c is the power of that prime. At this moment, both of them are 2. Then from one of the equation, our x2 should be written as a polynomial style like that with power with the factor 2, because it's q to the j. At this moment, q is 2, the prime factor, right? And c is 2, therefore it's only up to 1, right? 0 to 1, so we're expecting 2 terms for x2. Once again, aj must be either 0 or 1, because they must be less than the factor 2. Then it's easy to calculate a0 and a1 from that equations, because our equation a to the alpha to the a here times p minus 1 over q should be our beta to certain things, right? And at this moment is 0. So if a is 0, then it should congruent to 1 for modulo p. But if a is 1, then it's congruent to negative 1 for modulo p. So please keep this one in your mind. And for this whole process, you have to calculate this first. And another thing is, okay, how can you calculate 6 to the 4050? You cannot do that. That's why we need to use the Maple program. So once again, this number is small enough to calculate, right? But later we are going to use really huge number for that. So we need to separate into factors. Then we can use our program, Maple program, whatever it is. But we cannot do it with the original prime p. Okay, so that's the kind of main idea behind this Pollich-Hellman algorithm. Okay, so after we have that, let's apply these formulas we found. Beta to the p minus 1 over q should be like that. Every number is known. So this is that one. After you calculate with Maple, it's congruent to 8100, which must be negative 1 for modulo p. It's easy. Then this beta to the p minus 1 over q must be same as, do you remember? We have these formulas, right? Alpha to the a times p minus over q. We have only two choices of it, 0 or 1. So which one giving us negative 1 when a is 1, right? So at this moment it's for 0. So it should be 1 for a0. Then how about a2? We are looking for beta 1. By the formula, it should be like this. So beta is 7531, alpha is 6, and this a0 comes from this one, right? So we have to find this one by one, right? There's no jump. So we need this information. So plug 1 for a0, then it's alpha to the negative 1 only, is the inverse of 6 for this modular. So it becomes 8006, right? Then plug that one for b1 to calculate this, right? Then it becomes 1 finally. Therefore our a1 must be 0. because when we get 1 when a is 0, right? Okay, then this whole alpha is congruent to 1. Okay, so by that we can find the first value for x, which is written by x2 for modulo 2 2 is 1 by this formula plus 0, which is 1. So this one tells us we don't know what x is yet, but one thing is clear, this number should be congruent to 1 for modulo 4. For x3, we just do exactly same procedures with q is 3 and c is 4. So it takes more time because we have power 4. So the meaning is x3 is combination of these 4 terms, and we have all these unknown a0, a1, a2, a3 for these cases. So we have to do 4 times for similar procedures. Once again, at this moment, j must be 0, 1, or 2 because our power is the prime factor is 3. So it's easy to find these numbers first, right? When we have it. So from there, if a is 0, it's congruent to 1. If a is 1, it's congruent to that, right? If it's 2, congruent to that, right? So we found this all 3 different cases. So please keep this one in your mind. The answer should be 1, 5883 or 2217. Now for each beta, we just find out this. The first one, 2217. Therefore, you see that a must be 2. At this moment is the first one, so a0 must be 2. For a1, start with beta 1, becomes this one, so plug that one for beta j, then it becomes 1, therefore a1 must be 0, right? When a equals 0, we got 1. Okay. So if you plug that one for beta 2, right, once again, then it becomes this number, plug that one again, then it becomes 2217. You remember that a2 must be 2. So beta 2 should be beta actually 3 at this moment, so it's a typo. So a3 becomes 1. Please check by yourself this much. So altogether, our x3 is a combination of these 4 terms, and each of a0, 1, 2, 3 is 2, 0, 2, 1. So altogether is 47, which means our unknown so far x is congruent to 47 for modular 3 to the 4th or for 81. Now this is your homework assignment. It's in one of our exercise problems. So please find this fact yourself. It's only 5 squared. So you can imagine there are only a0, a1, that much, right? Okay, so you need to just find 2. And we found that x should be congruent to 14 for modulo 25. So we found 3 facts. Our x that we are looking for is congruent to 1 for modulo 4, it's congruent to 47 for modulo 81, congruent to 14 modulo 25. So using Chinese remainder theorem, we are going to find the x must be 689 for modular 81. Okay. And that's what you're looking for. Okay. So we found these numbers. And be careful, there are slight differences over here, right? So this is what we are looking for.